December 30th, 1941. Bethlehem-Fairfield Shipyard, Baltimore, Maryland. The SS Patrick Henry sat complete at her berth, 441 feet of welded steel ready for service. 8 months of construction had produced America's first Liberty ship. Traditional maritime experts examined the vessel with profound skepticism. Every major seam joining the hull plates had been welded rather than riveted, a technique the British Admiralty explicitly forbade for warship construction. Yet here stood proof that someone believed welding could work at unprecedented scale. 10 days earlier, Japanese aircraft had devastated Pearl Harbor. America had entered a war for which it was catastrophically unprepared. The nation possessed fewer than 200 ocean-going cargo vessels. Britain was starving. German U-boats prowled the Atlantic, sending Allied merchant ships to the ocean floor faster than traditional shipyards could possibly replace them. The mathematics were brutal and unforgiving. At conventional construction speeds of 6 to 8 months per vessel, the Allies would lose the Battle of the Atlantic before American industry could respond. Standing among the crowd of officials and shipyard workers was a reality few dared speak aloud. The welding technique that made the Patrick Henry possible represented not innovation born from confidence, but desperation wrapped in revolutionary thinking. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. One idea, dismissed as impractical by every established maritime authority, would determine whether convoys could reach Britain or whether Nazi Germany would starve the island nation into submission. The story of how welding transformed American shipbuilding began not in a shipyard, but at a Ford Motor Company assembly plant in Detroit, 14 months earlier. October 1940. Clay Bedford, chief engineer for industrialist Henry Kaiser, walked through Ford's River Rouge plant, watching automobile chassis move down production lines, workers installed, prefabricated components at each station with mechanical precision, engines dropped into frames, wheels bolted onto axles, bodies welded together from pre-manufactured sections. Bedford had come to Detroit because Kaiser faced an impossible challenge. In December 1940, Kaiser's company had signed contracts with the British government to build 30 cargo ships within 2 years. Kaiser had never built a ship. His career had been moving earth and pouring concrete. He had constructed the Hoover Dam, the Bonneville Dam, the Grand Coulee Dam. He knew heavy construction. He understood mass production. He had no experience whatsoever with maritime engineering. British vessels were sinking at catastrophic rates. German U-boats and surface raiders had sent approximately 3.6 million tons of Allied shipping to the bottom in 1940 alone. Traditional American shipyards, using methods unchanged since before the American Revolution, required an average of 230 days to construct a single cargo vessel. At that pace, German submarines would win through simple mathematics. They could sink ships faster than conventional methods could replace them. Bedford watched Ford workers weld automobile frames and bodies. The process was fast. The welds were strong. The workers were not master craftsmen who had spent years as apprentices. They were ordinary people who had learned specific welding tasks in weeks rather than years. He returned to California convinced that ships could be built the same way. The proposal Kaiser presented to the United States Maritime Commission in early 1941 shocked traditional shipbuilders. He proposed eliminating riveting entirely. For generations, ship construction had relied on rivets. Heated metal pins were hammered through overlapping steel plates to join them together. A skilled riveting crew working with perfect coordination could install perhaps 100 rivets per day. Each Liberty ship, a design required approximately 1 million rivets if built conventionally. Riveting accounted for 1/3 of total labor costs in traditional ship construction. Kaiser proposed using electric arc welding instead. The technique had existed since the late 19th century, but maritime authorities considered it unproven and dangerous for hull construction. The British Royal Navy explicitly prohibited welding on warship hulls. Vice Admiral Emery Land, chairman of the United States Maritime Commission, examined Kaiser's proposal with deep professional skepticism. His private correspondence preserved in the National Archives captured the maritime establishment's reaction. Welding has never been proven reliable for hull construction at this scale. The stresses on an ocean-going vessel in heavy seas are immense. Riveted joints have served maritime construction for over a century. Kaiser is proposing we bet America's supply lines on an unproven technology from a man who has never built a ship. The risk is enormous. Yet land also recognized desperation. German submarines were winning. In January 1941 alone, U-boats sank over 300,000 tons of Allied shipping. Britain's situation grew more desperate with each passing month. Food supplies dwindled, fuel reserves dropped. The island nation faced potential starvation if the supply lines could not be maintained. American shipyards using conventional methods would require decades to build enough vessels to offset losses. The decision to approve Kaiser's contract represented not confidence in his methods, but mathematical necessity. If traditional construction continued, the Allies would lose. Kaiser's approach might fail catastrophically, but conventional methods were already failing in slow motion. The gamble was authorized. Kaiser's experience with welding came from construction projects across the American West during the 1930s. He had used arc welding to join massive steel pipelines, carrying water across desert terrain. He had welded structural components for dams under conditions that demanded speed and reliability. The technique required less physical strength than riveting, making it accessible to workers who lacked years of specialized training. Most importantly, welding was faster. The decision to use welding carried profound implications beyond construction speed. Traditional shipyards recruited from established maritime communities where skills passed from father to son across generations. Young men served 4-year apprenticeships, learning comprehensive riveting skills. The pool of qualified workers was small and growing smaller as men enlisted in military service. Welding could be taught in weeks rather than years. Workers did not need to master every aspect of the craft. They needed to learn specific techniques for specific tasks they would perform repeatedly. A worker welding vertical seams on bulkheads did not need to know how to weld curved hull sections. Specialization replaced comprehensive skill, exactly as Ford's assembly lines had demonstrated with automobile production. The Richmond shipyard rose from empty mudflats along San Francisco Bay between January and December 1941. Kaiser's construction crews erected a facility that horrified traditional maritime engineers. Instead of the massive gantry cranes and longitudinal building ways that characterized established shipyards, Richmond featured open areas for prefabrication surrounding 7 parallel building ways. Railroad tracks crisscrossed the facility designed to move massive steel sections weighing up to 150 tons. Overhead cranes capable of lifting entire ship sections stood every 100 feet. John Riley, chief naval architect for Bethlehem Steel Corporation and a 30-year veteran of shipbuilding, visited the Richmond Yard in May 1941. His inspection report, marked confidential, contained both technical criticism and grudging professional admiration. Kaiser has violated every principle of efficient shipyard layout I learned in 3 decades of experience. His prefabrication areas are too large. His crane capacity is absurdly excessive. His building ways are too short for traditional construction methods. Yet I must acknowledge the facility is designed for exactly what he claims: rapid assembly of prefabricated sections. If his welding approach succeeds, this yard could revolutionize ship construction. If it fails, he has built the most expensive monument to hubris in American industrial history. The arrival of workers in summer 1941 provided the next revolutionary element. Kaiser advertised in newspapers across America, offering wages 20% above standard industrial rates and promising to train anyone willing to work. Traditional shipyards recruited experienced maritime workers. Kaiser recruited farmers, secretaries, housewives, laborers, anyone with hands willing to learn. The first training groups arrived in Richmond in August 1941. Women comprised a significant portion of the workforce from the beginning. Traditional shipyards employed women only in office positions. Kaiser hired women for production work, including welding. By 1943, women would comprise 30% of workers at Kaiser's Portland shipyards. In Richmond, they became known as Wendy the Welder rather than Rosie the Riveter. reflecting the technological shift that made their employment practical. Training programs condensed 4 years of traditional apprenticeship into 2 weeks of intensive instruction focused on specific tasks. Instructors taught vertical welding for bulkheads, horizontal welding for deck plates, overhead welding for ceiling sections. Workers learned one technique thoroughly rather than comprehensive welding knowledge. The simplification of complex tasks into repeated simple operations borrowed directly from assembly line manufacturing. Mary Carroll became the first woman hired as a welder at Kaiser's Portland shipyards in April 1942. Her 27-year-old son had died in the Battle of Bataan in the Philippines. She wanted to contribute to the war effort directly. Carroll learned to operate welding torches, read blueprints, and work with steel plates in just weeks. She worked alongside Jean Wild, the second woman welder hired. They shared a home with Carroll's family in Lake Oswego near Portland. Traditional maritime authorities watched this workforce with professional horror. These were not craftsmen. They were factory workers performing repetitive tasks with minimal training. Surely the ships they produced would be inferior, dangerous, unreliable. Quality would suffer catastrophically when inexperienced hands replaced generations of accumulated skill. The first Liberty ship keel laid at Richmond on April 14, 1941, just 3 months after groundbreaking. The SS Ocean Vanguard took 197 days to complete. Ship number 2 required 169 days. Ship number 5 took 128 days. Ship number 10 required 97 days. By spring 1942, Richmond was completing Liberty ships in 70 days on average. Something unexpected was occurring. Construction times fell dramatically as workers gained experience and as Kaiser's engineers refined the prefabrication process. Traditional shipyards watched with growing alarm as this untrained workforce achieved production speeds that matched and then exceeded their own highly skilled crews. The prefabrication approach that traditional builders had dismissed as impractical proved devastatingly effective. Instead of building ships from keel to deck in sequence, Kaiser's yards fabricated entire sections simultaneously across the facility. In one area, workers welded bottom hull sections. In another, bulkheads took shape. A third team assembled deck sections. A fourth built the superstructure housing. When sections were complete, massive cranes lifted them to the building ways where welders joined them together. Traditional construction had one crew working on one ship progressing from bottom to top. Kaiser's method employed dozens of crews working on different sections of the same ship simultaneously. The ship came together like an enormous 3-dimensional jigsaw puzzle rather than being built piece by piece. Each Liberty ship required approximately 50 miles of welding. The welds joined steel plates without the overlapping required for riveting, saving steel. Welding required less physical strength than swinging, riveting hammers, making it accessible to smaller workers, including women. Most importantly, welding was dramatically faster than riveting. One welder could accomplish work that required a 3-person riveting team. By November 1942, Kaiser's Richmond Shipyard No. 2 prepared to demonstrate the ultimate potential of his methods. The SS Robert E. Peary would become the most famous Liberty ship never to see combat. On Sunday morning, November 8, 1942, workers laid the keel for a standard Liberty ship. What happened next would establish a record that stands to this day for vessels of that size. The entire shipyard focused on one vessel with one goal: demonstrate beyond any doubt that mass production techniques could achieve speeds traditional maritime experts claimed impossible. Prefabricated sections moved to the building way with precision timing. Welders worked in rotating shifts around the clock. Cranes lifted massive steel assemblies into position. Welding torches flashed continuously as seams joined. The superstructure rose. The decks took shape. The engine installed. Equipment fitted. Painting completed. On Thursday, November 12th, the SS Robert E. Peary slid down the ways into San Francisco Bay. 4 days, 15 hours, and 29 minutes after the keel was laid. Traditional shipyard representatives who had come to witness the event stood in stunned silence. What had just occurred violated every assumption they held about ship construction timeframes. The Peary was not a partially completed vessel rushed to launching. It was a fully functional Liberty ship ready for service. The crew boarded that same day and sailed within 48 hours. The ship served throughout the war, carrying cargo across both Atlantic and Pacific. It survived the conflict and continued commercial service until 1963, when it was finally scrapped, having far exceeded its original 5-year design life. The record was never seriously attempted again. 4 days remained the permanent benchmark, demonstrating what organized systems and dedicated workers could achieve when traditional limitations were questioned. Yet the Peary was never the point. It was demonstration, proof of concept, validation that the methods worked. The real achievement was the sustained production that followed. By January 1943, American shipyards were completing 3 Liberty ships every 2 days. The peak came in 1944, when Kaiser's 7 shipyards employed 100,000 workers producing ships at rates that eclipsed every other nation's combined output. The ships themselves embodied revolutionary simplicity. Liberty ships measured 441 feet long and 56 feet wide. They displaced 10,500 tons when loaded. A triple expansion steam engine, obsolete technology dating to the 19th century, powered them to a maximum speed of 11 knots. This was slower than modern vessels, but speed was not the primary consideration. The engines were simple, rugged, familiar to seamen, and most importantly, easy to manufacture. 18 different companies could produce them because the design required no precision machining of complex turbine gears. Each Liberty ship could carry 9,000 tons of cargo inside its hull, plus additional equipment on deck. 2,840 jeeps, 440 tanks, 230 million rounds of rifle ammunition, or 10,000 tons of mixed supplies, fuel, ammunition, food, medical equipment, spare parts, everything an army required to fight across oceans. The cargo capacity of a single Liberty ship exceeded the carrying capability of 300 railroad freight cars. The ships became floating warehouses, delivering the material foundation of Allied military power to every theatre of war. Without them, armies in Europe, Africa, and the Pacific would have starved for ammunition, fuel, and food. Production statistics tell the story of transformation. In 1941, American shipyards delivered 60 Liberty ships. In 1942, production reached 597 vessels. In 1943, 1,368 ships launched. Peak production came in March 1943, when American yards completed 140 Liberty ships in a single month, 3 per day on average for 30 consecutive days. The transformation extended far beyond ship construction. Kaiser built entire communities to house workers. The city of Richmond, California, grew from a population of 23,000 in 1940 to over 100,000 by 1943, driven entirely by shipyard employment. Kaiser constructed Vanport City in Oregon, which briefly became the state's second-largest city, with a population exceeding 40,000, all working in shipyards or supporting industries. To provide medical care for his massive workforce, Kaiser partnered with physician Sidney Garfield to establish prepaid healthcare programs. Workers paid a small weekly fee in exchange for comprehensive medical services. This innovation evolved into Kaiser Permanente, which by the early 21st century served over 12 million members, demonstrating how wartime necessity created peacetime institutions. The scale of industrial mobilization defied comprehension. 18 American shipyards built Liberty ships between 1941 and 1945. Kaiser's 7 yards produced 821 Liberty ships, plus 219 Victory ships, the improved design that followed. In total, American yards delivered 2,710 Liberty ships, easily the largest number of vessels ever produced to a single design. Each ship required approximately 250,000 parts prefabricated across the country, then assembled in the shipyards. Steel mills produced plates to standardized specifications. Foundries cast engine components. Electrical manufacturers supplied wiring systems. Pump makers delivered mechanical systems. The entire American industrial economy coordinated to feed the shipyards with components. The labor force transformation was equally profound. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Over 1.5 million workers learned shipbuilding skills during the war. At the peak of production in summer 1944, Kaiser's yards alone employed 100,000 workers. 28,000 were women, comprising 30% of the workforce. African Americans migrated from southern states seeking employment in integrated shipyard work crews, permanently changing the demographic composition of West Coast cities. Women welders became essential to production. Training courses lasted 8 weeks for comprehensive skills, or as little as 1 week for specific tasks. After completing training, women went directly into production work. Mildred Orpid, who had worked at a telephone company in New Orleans, saw an advertisement for welding training in summer 1942. She enrolled immediately, trained for 2 months, and went straight to work at Delta Shipbuilding. She earned $1.25 per hour for 8-hour shifts, extraordinary wages that allowed her to save $2,500 during her wartime service. The work was difficult, dangerous, and exhausting. Welders suffered burns from falling rods, worked in confined spaces inside hull sections, operated heavy equipment, and faced constant pressure to maintain production speed. Yet the wages, the patriotic purpose, and the opportunity to contribute meaningfully to the war effort drove sustained commitment. Brunswick, Georgia's J.A. Jones Shipyard launched 85 Liberty ships between March 1943 and March 1945. The Surrency sisters, Nanelle, Carabeth, and Laurie, all became welders at the Brunswick yard after relocating from Jesup, Georgia. Carabeth learned welding in 1 week of training, then spent a month mastering flat welding, vertical welding, and overhead welding. The sisters worked alongside thousands of others in a community transformed entirely by wartime industrial production. The mathematical impact on the Battle of the Atlantic was decisive. German U-boats sank approximately 14.1 million tons of Allied shipping during the entire war, roughly 70% of all Allied maritime losses. The most successful year for German submarines was 1942, when they sank over 6 million tons in the Atlantic alone. Admiral Karl Dönitz, commander of the German submarine fleet, believed his U-boats could sink Allied vessels faster than they could be replaced. The tonnage war strategy required sinking 700,000 gross registered tons per month to overwhelm Allied shipbuilding capacity. The Germans achieved that target in only 1 month, November 1942. But by then, American shipyards were already turning the mathematical tide. In September 1942, American and Canadian yards delivered 713,000 tons of new merchant shipping, while only 500,000 tons were lost to all causes. From that point forward, with one exception, Allied shipbuilding exceeded losses every single month until the war's end. The Liberty ships delivered cargo totaling over 200 million tons during the war. More than 2/3 of all supplies leaving the United States traveled aboard Liberty ships. They carried fuel to England, ammunition to North Africa, food to the Soviet Union via Murmansk, and supplies to the Pacific Islands where American forces fought their way toward Japan. The ships themselves became weapons through their sheer numbers. U-boats could sink individual vessels, but they could not sink ships faster than American yards produced them. Admiral Chester Nimitz, commander of the Pacific Fleet, reflected on the strategic impact in his post-war memoir published in 1960. We fought across 5,000 miles of Pacific Ocean, supplied by ships built faster than the enemy could sink them. Japan's military planners assumed American industrial capacity was impressive but finite. They believed if they sank enough ships, eventually American logistics would collapse and we would be forced to negotiate. They failed to account for Henry Kaiser. By 1944, we were replacing shipping losses faster than they could inflict them. The mathematics of attrition favored the side that could build 3 ships daily over the side that could sink 2 ships daily. Industrial capacity, not martial valor, determined the outcome. The Liberty ships themselves were not beautiful vessels. President Franklin Roosevelt called them dreadful-looking objects. Time magazine dubbed them ugly ducklings. The design prioritized function over form, simple lines, utilitarian construction, no aesthetic considerations whatsoever. They were cargo carriers built for a specific purpose under extreme time pressure, yet their very ugliness testified to focused determination. Every design choice served efficiency, speed of construction, and cost reduction. The ships cost approximately $2 million each to build, remarkably inexpensive considering their size and capability. By comparison, a single heavy bomber cost $400,000. A Liberty ship delivered far more strategic impact than any individual aircraft. The ships were designed for 5-year operational lifespans, yet many served for decades. Some Liberty ships remained in commercial service into the 1970s and 80s, carrying cargo long after their intended retirement. But the production miracle masked a crisis that emerged in winter 1942 and 1943. The ships were breaking, not from torpedo damage or battle action, but spontaneously, catastrophically, in conditions that should have been routine. On January 16, 1943, the SS Schenectady sat quietly at dock in Portland, Oregon. She was a brand new Liberty ship, barely 10 weeks old, fresh from Kaiser's shipyards. No enemy action threatened her. No storm battered her hull. The morning was calm, the water still. Then, without warning, a sharp crack echoed across the harbour. Within moments, the entire vessel fractured completely in two. The hull split from deck to keel as if sliced by an invisible blade. Sailors scrambled as bow and stern sections sagged in opposite directions, the ship's back broken while tied safely to the pier. The Schenectady was not alone. That same winter, the SS John P. Gaines broke apart in calm seas. The SS Esso Manhattan, a tanker built using identical welding methods, cracked so severely her crew abandoned ship in panic. Between 1943 and 1944, more than 2,500 Liberty ships reported serious structural failures, hull cracks, deck fractures, catastrophic splits. At least 19 vessels broke completely in half. 3 simply vanished at sea, disintegrating so rapidly they could not send distress signals. These were not war casualties. These were ships committing structural suicide. The fractures typically started at sharp corners, hatch openings, gun mounts, the squared-off design features of the hull. Once a crack initiated, it propagated through the welded hull plates at terrifying speed, sometimes racing the entire length of a ship in seconds. Traditional riveted construction contained crack propagation because rivets provided discrete connection points. Welded hulls were continuous, allowing cracks to run without impediment. The Maritime Commission convened emergency investigations. Metallurgists examined failed sections under microscopes. Engineers reviewed stress calculations. Naval inspectors crawled through damaged hulls with measuring instruments. Everyone searched for the culprit: bad steel, faulty welds, design flaws, inadequate quality control. Ships continued splitting while committees debated. Sailors grew terrified of their own vessels, knowing the hull beneath their feet might unzip without warning in cold Atlantic waters. Initial suspicions fell on the shipyards, which had used inexperienced workers and rushed production, but examination of the welds themselves revealed they were sound. The steel met specifications. The designs came from proven British blueprints, yet Liberty ships were fracturing in ways riveted vessels never did. The answer emerged from metallurgical analysis conducted by Constance Tipper at Cambridge University. The fractures were not caused by faulty welding technique, but by the inherent properties of the steel in cold water conditions. The mild steel used in Liberty ship construction became brittle at low temperatures. In the cold North Atlantic, the steel lost its ductile properties. Combined with stress concentrations at corners and openings, the brittle steel could not absorb shock loads. Cracks initiated and propagated catastrophically. The welding itself contributed to the problem in ways no one had anticipated. Every weld created residual stress in the metal as the hot weld bead cooled and contracted. Traditional riveting did not introduce significant residual stress. Welded construction locked internal stresses into the structure. When welded ships hit cold water, the combination of brittle steel and residual stress created perfect conditions for catastrophic fracture. The solution required multiple changes. Engineers redesigned hull features, eliminating sharp corners and adding crack arrest features, steel straps that could stop crack propagation. They specified better steel with improved low-temperature toughness. They widened frame spacing from 30 inches to 36 inches, making the structure less rigid and more able to flex. Most importantly, they developed improved welding procedures to minimize residual stress. The success of Victory ships, introduced in 1944, incorporated all these improvements. Victory ships were slightly larger, significantly faster with turbine engines, and critically, they were built with improved welding procedures that reduced internal stress. 531 Victory ships were constructed between 1944 and 1946. Not one broke in half. The Liberty ship's structural failures killed crews, destroyed cargo, and undermined confidence in American shipbuilding. Yet the response demonstrated industrial resilience. Engineers identified problems, developed solutions, and implemented changes while maintaining production. The lessons learned from Liberty ship failures revolutionized understanding of metal fatigue, stress concentration, and fracture mechanics. Modern engineering codes incorporate requirements descended directly from analysis of Liberty ship cracks. By war's end, Liberty ships had delivered more than just cargo. They had demonstrated that industrial revolutions happen not through incremental improvements, but through fundamental reimagining of processes. They proved that ordinary people, given training and opportunity, could achieve extraordinary results. They validated that complex products previously requiring years of craft tradition could be manufactured in weeks using systematized methods. The 2,710 Liberty ships built between 1941 and 1945 carried more than military supplies across oceans. They carried proof that traditional limitations were not immutable laws, but assumptions that could be challenged. They demonstrated that industrial capacity was not fixed, but could be created rapidly when necessity and innovation combined. The welding revolution Kaiser pioneered extended far beyond shipbuilding. The techniques refined under wartime pressure became standard in structural steel construction, petroleum refining equipment fabrication, and pressure vessel manufacturing. Modern pipelines, refineries, power plants, bridges, and industrial facilities all use welding procedures descended from methods developed in Liberty ship construction. The organizational principles of parallel production, simplified specifications, and rapid worker training became foundational concepts in operations management and industrial engineering education. The workers themselves carried forward lessons of wartime experience into decades of peacetime achievement. Women who had welded ships returned to traditional roles after the war, but they carried with them knowledge that they could master technical skills, earn substantial wages, and contribute meaningfully to large industrial projects. That knowledge influenced the next generation's expectations about women's capabilities and opportunities. African American workers who had found employment in integrated shipyards used that experience to challenge discriminatory practices in other industries. The wartime integration of production work, while incomplete and imperfect, demonstrated that racial integration could function effectively when economic necessity demanded it. The Liberty ships are mostly gone now, scrapped decades ago, or resting on ocean floors. But the revolution they represented endures. In every modern shipyard using prefabrication techniques, in every training program teaching specific skills quickly rather than broad expertise slowly. In every manufacturing facility organizing work in parallel rather than sequential processes. In every manager questioning whether impossible truly means impossible, or simply means nobody has figured out how yet. Henry Kaiser proved that industrial revolutions require not just new technologies, but willingness to question fundamental assumptions. Traditional shipbuilders knew their craft thoroughly. They understood methods that had evolved over centuries. Their expertise was genuine and their skepticism reasonable. But their expertise became limitation when it prevented consideration of radically different approaches. Kaiser's ignorance of shipbuilding tradition became his advantage. He did not know that ships could not be built like automobiles. He did not understand that welding was unsuitable for hull construction. He did not recognize that trained workers required 4-year apprenticeships. Not knowing these truths, he attempted methods experts claimed impossible, and the methods worked. The lesson extends beyond World War II emergency production. It suggests that perceived limitations on capability often reflect conceptual constraints rather than physical impossibilities. Industries accept conventional wisdom about production limits, skill requirements, and organizational structures until someone ignorant of those constraints attempts something different and succeeds. The Liberty ship story ultimately testifies to human capability when freed from traditional limitations and empowered by necessity. The ships themselves mattered, certainly. They helped win the war by delivering supplies faster than enemies could destroy them. But what their construction proved mattered more. Ordinary people achieved extraordinary results because someone believed they could and organized systems, allowing them to prove it. From December 1940, when Kaiser signed his first contract knowing nothing about shipbuilding, to November 1942, when the Robert E. Peary launched after less than 5 days of construction, to September 1945, when the last Liberty ship was delivered, Kaiser demonstrated that breakthroughs come not from incremental improvements, but from fundamental reimagining of possibilities. The 2,710 Liberty ships built in those 4 years carried more than cargo. They carried validation that human ingenuity, when unshackled from tradition and challenged by necessity, can accomplish what conventional wisdom claims impossible. They proved that revolutions begin when someone asks not whether something can be done, but rather why it has not been done already, and then proceeds to do it. The welding innovation that made Liberty ships practical transformed not just shipbuilding but manufacturing philosophy itself. Before Liberty ships, production methods evolved slowly through incremental refinement. After Liberty ships, industrial managers understood that revolutionary change was possible when necessity demanded it, and when leadership was willing to challenge fundamental assumptions. The Pacific War was won on beaches and in naval battles, certainly, but it was made possible by industrial capacity that delivered supplies faster than combat could consume them. The European theatre was liberated by soldiers and airmen, undoubtedly, but those forces moved on Liberty ships carrying fuel, ammunition, food, and equipment that sustained military operations across continents. The mathematical reality was simple and decisive. Allied forces could be supplied faster than Axis forces could destroy supplies. That mathematical advantage, created by welders in Richmond and Portland and Brunswick and Baltimore, determined strategic outcomes as surely as any battle. Industrial capacity became military power. Production speed became strategic advantage, and ordinary workers became the foundation of victory. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.